Tonight, we're going to explore one of the strangest things in all of physics. Imagine grabbing two objects and trying to pull them apart. You'd expect that with enough force, they'd eventually separate. That's how everything in your experience works. But deep inside every atom in your body, there are particles called quarks. And when you try to pull two quarks apart, something impossible happens. The harder you pull, the stronger the resistance becomes. And if you pull hard enough, instead of finally breaking free, the energy you pumped into separating them creates entirely new particles out of the vacuum itself. You never get a free quark. Ever. No one in the history of science has ever isolated one. And by the end of this journey, you're going to understand exactly why the universe won't allow it. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know. Matter. The stuff that makes up everything around you. Your body, the ground beneath your feet, the device you're using to listen to this right now. All of it is matter. And for most of human history, the question of what matter is actually made of was answered by philosophy, not by science. About 2,400 years ago, the ancient Greek philosopher Democritus proposed an idea. He suggested that if you took any piece of matter and kept cutting it in half, smaller and smaller and smaller, you would eventually reach something so small that it could not be divided any further. He called this smallest possible piece atomos, which means uncuttable. And for more than 2,000 years, that idea sat there untested. A thought experiment frozen in time, waiting for technology to catch up. Then the 19th century arrived and everything changed. Chemists and physicists built up overwhelming evidence that atoms were real. They had definite sizes, definite masses, and they combined in precise ratios to form molecules and compounds. The periodic table organized them by their properties, revealing deep patterns in how the elements behave. Atoms were no longer philosophy. They were measurable, countable, physical objects. But here is the irony that would reshape all of physics. Those supposedly uncuttable particles turned out to be very much cuttable. In 1897, a British physicist named J.J. Thomson discovered the electron, a tiny particle carrying a negative electric charge that was clearly a piece of something larger. If you could pull an electron out of an atom, then the atom had internal structure. It was not the bottom of the ladder. It was just another rung. Over the following decades, the picture filled in rapidly. Ernest Rutherford fired fast-moving particles at sheets of thin gold foil and discovered something astonishing. Almost all the particles passed straight through the foil, as though it were empty space. But a tiny fraction bounced back violently, as though they had struck something unimaginably dense. Rutherford realized that nearly all of an atom's mass is concentrated in a minuscule central region he called the nucleus. That nucleus, it turned out, contains positively charged particles called protons. A few years later, the neutron was discovered, a particle of nearly the same mass as the proton but carrying no electric charge at all. The modern picture of the atom snapped into focus. A dense nucleus of protons and neutrons, surrounded by a cloud of orbiting electrons. 1 proton gives you hydrogen, 6 protons give you carbon, 26 protons give you iron, 79 protons give you gold. The neutrons sit alongside the protons in the nucleus. contributing mass and helping hold the whole thing together through forces we will return to later. For a time, this seemed like the end of the road. Protons and neutrons appeared to be truly fundamental, the smallest building blocks of the material world, the floor beneath the floor, the point beyond which you could not go any deeper. But physics has a habit of pulling the rug out from under you exactly when you think you have found solid ground. In the 1950s and early 1960s, something unexpected started happening. Physicists built more powerful particle accelerators, enormous machines that could smash protons and other particles together at incredible energies. And when they did, they found new particles. Not just a few new particles, an avalanche of them. Pions, kaons, sigma particles, omega particles, dozens upon dozens of previously unknown objects with exotic names and peculiar properties. By the early 1960s, the list had grown past 100 distinct particles. It was chaos. There seemed to be no organizing principle, no reason why there should be so many supposedly fundamental objects. The situation grew worse every year as accelerators got more powerful and more particles kept appearing. Something had to give. There had to be a deeper layer. If there were over 100 particles, maybe they were not all fundamental. Maybe they were combinations of something simpler, the way thousands of words are built from a small alphabet. And in 1964, two physicists working independently arrived at exactly that conclusion. Murray Gell-Mann at the California Institute of Technology and George Zweig, working at CERN in Switzerland, both proposed that protons, neutrons, and all those other particles were not truly fundamental. They were built from something smaller. Gell-Mann called these smaller building blocks quarks, a word he borrowed from a whimsical line in James Joyce's novel Finnegan's Wake. Zweig called them aces. The name quarks is the one that stuck. The idea was elegant and powerful. Instead of memorizing over 100 fundamental particles, you needed just a small number of quarks. And the different combinations of those quarks produced every particle that had been discovered. A proton is made of 3 quarks, a neutron is made of 3 quarks, a pion is made of a quark, and an antiquark. All of these composite particles, those made of quarks bound together by the strong interaction, belong to a family called hadrons. A hadron is any particle that is built from quarks. Protons are hadrons, neutrons are hadrons, pions and kaons are hadrons. The alphabet had been found. The particle zoo was not a random collection of unrelated creatures, but a structured language built from a small set of fundamental letters. The pattern behind the chaos became visible. Today, we know that there are 6 types of quarks. Physicists call these types flavors, and their names might sound whimsical because they are. The 6 flavors are up, down, strange, charm, bottom, and top. These names carry no deep physical meaning, but the physics they describe is anything but casual. Here is what matters most for our story. Ordinary matter, the matter that makes up everything you see and touch and interact with every day of your life, uses only the 2 lightest flavors, up and down. A proton contains 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up quark. That is it. Every atom in your body, every atom in the earth, in the air, in the oceans, is built from protons and neutrons. And those protons and neutrons are themselves built from just up quarks and down quarks. 2 flavors out of 6 account for essentially all the visible matter in the universe. The heavier quarks, strange, charm, bottom, and top, are produced in high-energy collisions and in extreme astrophysical environments, but they are unstable. They decay rapidly into the lighter up and down quarks. They do not linger long enough to form everyday matter. The top quark, the heaviest of all six, has a mass roughly 185 times the mass of an entire proton. It is so massive and so short-lived that it exists for less than a trillionth of a second before falling apart. But it is real. It has been detected and measured with precision at particle accelerators. Every single flavor predicted by the theory has been found experimentally. Each quark also carries a fractional electric charge, which seemed bizarre when it was first proposed. Up quarks carry a charge of plus 2/3. Down quarks carry a charge of minus 1/3. These fractions might appear odd, but watch what happens when you add them up. Inside a proton, you have 2 up quarks and 1 down quark. Plus 2/3, plus 2/3, minus 1/3. That equals plus 1, which is exactly the measured electric charge of a proton. For a neutron, 2 down quarks and 1 up quark. Minus 1/3, minus 1/3, plus 2/3. That equals 0, which is exactly the measured charge of a neutron. Charges that have seemed arbitrary for decades suddenly had a clean explanation. Everything fit together. But electric charge is not the only charge quarks carry. There is another property, one that has no analogy in your everyday experience, one that governs a force far more powerful than the electromagnetic force that holds atoms together. This property is called color charge, and I need to be clear about something immediately. Color charge has nothing to do with color in the visual sense. Quarks are not red or blue or green. They are far too small to interact with visible light. They do not have a color you could see with your eyes or with any instrument. The name was borrowed from the language of visible color purely because the mathematics happened to work in a way that was loosely reminiscent of how primary colors combine. Physicists could have called them type A, type B, and type C, or apple, banana, and cherry. The physics would be identical. But the color analogy caught on, and now it is the standard terminology used worldwide. So whenever you hear the words color charge in this story, understand that it is a label for a quantum property of quarks and gluons. A label that has nothing to do with how anything looks. Nothing more. Every quark carries one of 3 color charges: red, green, or blue. Every antiquark carries one of 3 corresponding anti-color charges: anti-red, anti-green, or anti-blue. These are not 3 different strengths of the same charge, the way you might have a large positive charge and a small positive charge in electricity. These are 3 genuinely distinct types of charge. Each one is as different from the others as electric charge is from having no charge at all. Color charge exists in a richer mathematical space than the electric charge. Electromagnetism has one type of charge with 2 signs, positive and negative. The strong interaction has 3 types of charge, each with its own anti-charge. This richer structure is one of the reasons the strong force behaves so differently from anything in everyday life. And here is the crucial rule that color charge imposes on the universe. Only color-neutral combinations of quarks are ever allowed to exist as observable, free particles. Nothing carrying a bare color charge has ever been detected in isolation. Not once in the history of experimental physics. This rule is not a guideline. It is not a tendency. It is absolute. A particle can achieve color neutrality in 2 main ways. The first is to combine all 3 colors. Red plus green plus blue yields a color neutral result. This is loosely analogous to mixing the three primary colours of light to produce white, which is why the colour label was chosen in the first place. This is how baryons work. A proton contains 3 quarks, one red, one green, and one blue. Their colour charges cancel, and the proton as a whole carries no net colour charge. A neutron works the same way. 3 quarks, 3 colours, colour neutral overall. The second way is to pair a colour with its anti-colour. Red combined with anti-red is colour neutral. Green combined with anti-green is colour neutral. Blue with anti-blue, the same. This is how mesons work. A meson contains 1 quark and 1 antiquark. The quark carries a colour, the antiquark carries the matching anti-colour, and together they form a colour-neutral composite. There is no way around this. No lone quark carrying a single bare colour charge by itself has ever been detected as a free particle. Every quark ever observed has been locked inside one of these colour-neutral combinations. This rule holds at every energy ever probed, in every experiment ever conducted, in every environment ever studied. And understanding the mechanism behind it is what will take us into the strangest territory in all of physics. To understand why quarks are permanently imprisoned, we need to talk about the force that holds them, and that means we need to talk about gluons. In electromagnetism, the force between electrically charged particles is carried by photons. When 2 electrons repel each other, they are exchanging photons. The photon is the force carrier, the messenger particle that transmits the electromagnetic interaction from one charged object to another. This framework, where forces arise from the exchange of particles, is one of the deepest ideas in modern physics. It applies not just to electromagnetism, but to all the fundamental interactions. The strong interaction works on the same basic principle. The force between colour-charged quarks is carried by particles called gluons. When 2 quarks interact, they exchange gluons, just as 2 electrically charged particles exchange photons. A quark emits a gluon, another quark absorbs it, and the exchange generates a force between them. The theory that describes this interaction in full mathematical detail is called quantum chromodynamics. The name means exactly what it sounds like. Chromo comes from the Greek word for colour, and dynamics means the study of forces and motion. Quantum chromodynamics is the quantum theory of how colour charges interact. It is one of the central pillars of the standard model of particle physics, the most successful and most precisely tested framework for understanding the fundamental forces of nature ever constructed. But here is where quantum chromodynamics reveals something that makes it fundamentally qualitatively different from electromagnetism. This single difference is the key to everything we are going to explore tonight. It is the reason quarks behave in ways that nothing else in your experience ever does. And once you understand it, the rest of the story follows with a kind of terrifying inevitability. Photons, the carriers of the electromagnetic force, are electrically neutral. They carry no electric charge whatsoever. A photon is indifferent to the force it carries. This has a profound consequence. Because photons carry no charge, they do not interact with each other. You can cross 2 beams of light and neither one bends or scatters or affects the other in any way. Photons are messengers that deliver letters but never read them. They transmit the electromagnetic force between charges, but they do not feel it themselves. Gluons are the opposite. Each gluon carries colour charge. Specifically, each gluon carries a combination of a colour and an anti-colour. There are 8 distinct types of gluons, each carrying a different colour charge combination. And because gluons carry color charge, they do not merely transmit the strong force, they participate in it. A gluon can interact with another gluon. A gluon can emit more gluons. Two gluons can scatter off each other. The force carriers of the strong interaction feel the very force they carry. This might sound like a technical detail. It is not. It is the single most important fact about the strong interaction. It changes everything. In electromagnetism, the force carriers are passive. They deliver the interaction but do not contribute to it. In quantum chromodynamics, the force carriers are active participants. They do not just carry the strong interaction, they amplify it, complicate it, and fundamentally transform how it behaves at different distances. The self-interaction of gluons is what ultimately leads to confinement, and it is what creates the bizarre situation where trying to pull quarks apart does not free them, but instead creates entirely new particles out of the energy you supplied. To appreciate how different this makes the strong force, compare it carefully with electromagnetism. Imagine two oppositely charged particles, a positive charge and a negative charge, separated by some distance. Between them, an electric field exists. The field lines spread outward through space in all directions like the ribs of an open umbrella. As you pull the charges farther apart, the field lines fan out over a larger and larger volume of space. Because the field energy is spreading over a bigger area, the intensity weakens. The force between them drops. Double the distance and the force drops to 1/4 of what it was. Triple the distance, the force drops to 1/9. This is the familiar inverse square law. It is why electromagnetism weakens smoothly with distance. The field disperses, the energy dilutes, the grip loosens. You might expect the color field between two quarks to behave the same way. Spread out, dilute, weaken. But it does not. Because gluons interact with themselves and with each other, the color field between separating quarks does something entirely different. And that difference is where the story takes its most dramatic turn. Before we explore what happens at larger separations, we need to understand something remarkable about what happens at very short distances. Because the strong interaction has a counterintuitive property at tiny scales that earned 3 physicists the Nobel Prize. When two quarks are extremely close together, essentially sitting on top of each other, the strong interaction between them becomes weak. Not just slightly reduced, genuinely weak. The quarks behave almost as though they were free particles, barely interacting at all. They rattle around at short distances with almost no resistance from the color force. This behavior is called asymptotic freedom. At asymptotically short distances, quarks approach freedom. The discovery of this property in 1973 by David Gross, Frank Wilczek, and David Politzer was one of the most important breakthroughs in the history of particle physics. It earned all three the Nobel Prize in Physics in 2004. Asymptotic freedom sounds like a contradiction. The strong force becomes weak, but the explanation lies in those self-interacting gluons. In quantum field theory, the space around any charge is alive with quantum fluctuations, temporary disturbances that briefly pop into existence and then vanish. Around an electrically charged particle, these fluctuations tend to screen the charge, making it appear weaker at long distances and stronger at short distances. This is a well-understood effect in electromagnetism called charge screening. The virtual particle-antiparticle pairs that constantly appear and disappear around a charge partially shielded, blunting its influence at greater distances. But the gluon fluctuations around a color charge do the opposite. Instead of screening the color charge, they anti-screen it. The quantum fluctuations produced by gluon self-interactions make the effective color charge appear stronger at longer distances and weaker at shorter ones. At the extremely short distances probed by very high energy collisions, the effective color charge becomes so small that quarks interact only feebly. They are almost free. This is not just theoretical. At particle accelerators, physicists have confirmed asymptotic freedom through decades of increasingly precise experiments. The deep inelastic scattering experiments at the Stanford Linear Accelerator Center in the late 1960s and early 1970s were among the first to reveal this directly. These experiments fired high-energy electrons at protons and measured how the electrons scattered. The patterns were exactly what you would expect if the electrons were bouncing off small, nearly free, point-like objects inside the proton. Those objects were the quarks. They were there, they were real, and at those short distances and high energies, they were barely interacting with each other. It was among the first direct evidence that quarks were real, physical constituents of the proton, not just mathematical abstractions that made the equations work. Because the strong interaction becomes weak at short distances, physicists can actually use their standard mathematical tools to calculate what happens in high-energy collisions. The techniques of perturbation theory, where you treat the interaction as a small correction, work beautifully when the coupling is small enough. And the predictions match experiments with stunning precision. But now comes the other side of that coin. And it is the side that changes everything. As quarks move farther apart, the effective strength of the color interaction does not keep diminishing. It reverses course. The interaction gets stronger, not gradually, not gently. It gets dramatically, overwhelmingly stronger as the distance grows. The anti-screening effect that weakened the interaction at short distances now works in the opposite direction. At the larger separations relevant to the interior of protons and neutrons, distances of roughly 1 femtometer, which is 1 quadrillionth of a meter, the coupling between quarks and gluons becomes enormous. The mathematical tools that worked so elegantly at short distances collapse completely. Perturbation theory, the approach of treating the interaction as a small correction, fails because the interaction is no longer small. It is not a correction to anything. It is the dominant feature of the system. This regime is called non-perturbative, and it is extraordinarily difficult to study analytically. It is the regime where confinement lives. Think about what this means. Every other fundamental force in nature weakens with distance. Gravity weakens. Electromagnetism weakens. The weak nuclear force operates only over an unimaginably tiny range, but the strong interaction between color charges gets more powerful as the quarks try to separate. The universe seems to enforce a rule built into its most fundamental laws. Color charges must not be pulled apart, and the harder you try, the more ferociously the universe pushes back. This behavior has no parallel in everyday experience. Nothing in the world you interact with on a daily basis works this way. It is unique to the strong interaction, and it is entirely caused by that one critical difference we discussed. The fact that gluons carry color charge and interact with themselves. The consequence is confinement. Quarks are permanently confined inside hadrons. No experiment in the history of physics has ever detected a free, isolated quark, and the search has been exhaustive. Physicists have looked for free quarks in cosmic rays. They have looked in deep sea water. They have analysed lunar samples brought back by the Apollo missions. They have looked in meteorites, in ordinary rocks, in every kind of material imaginable. They have searched for particles carrying the fractional electric charges, the plus 2/3 or minus 1/3. That would announce the presence of a bare quark outside a hadron. The answer has always been the same. Nothing. No isolated quark has ever been found, anywhere, at any energy, in any environment. At the most powerful particle accelerators ever built, physicists have pumped enough energy into individual collisions to create hundreds of new particles at once. They have probed distances so short that the quarks inside protons appear to move freely, beautifully confirming asymptotic freedom at close range. But no quark has ever flown out of a collision by itself. Every quark produced at high energy immediately becomes part of a new hadron, before anything resembling an isolated quark can be detected. The confinement is total, it has no observed exceptions. And yet, here is the deepest paradox. We know quarks are real. The evidence is overwhelming. Every prediction of the quark model has been confirmed. We can measure quark properties with extraordinary precision. Their masses, their electric charges, their color charges, their quantum numbers, their interactions. The entire standard model of particle physics, tested and verified by thousands of experiments across decades, rests on the existence of quarks and gluons. If quarks did not exist, none of our calculations would match the data. The framework would collapse. But you can never hold one. You can never isolate one. You can never extract a single quark and study it alone. They are real, but permanently imprisoned, detectable through their effects, but never directly liberated. It is as though you could hear someone's voice through a thick wall, learn everything about them, their name, their age, the precise details of their life, but the door cannot be opened. The wall is permanent. It is not a door that happens to be locked. It is a wall that does not permit a door to exist. You might be tempted at this point to think of confinement as simply a very powerful version of a familiar force, like a spring that is just too strong for us to stretch, like a chain that is just too tough for us to break. If that were the case, then with enough energy, you could eventually overcome it. You could pull hard enough and the quarks would snap free. After all, that is how everything else in your experience works. Pull hard enough on anything and it breaks. Ropes break, chains break, chemical bonds break. The nuclear forces that bind protons and neutrons together inside an atomic nucleus can be overcome with enough energy. Nuclear fission is exactly that process, supplying enough energy to break a nucleus apart. Why should the force between quarks be any different? Because it is different, fundamentally different. What happens when you try to pull two quarks apart does not follow the pattern of any force you have encountered in your life. The energy you supply does not accelerate one quark away from the other into freedom. Instead, it is absorbed by the color field between them. The field grows more concentrated, more energetic, more intense. The harder you pull, the more energy you feed into that field. And the field holds it, stores it, builds it up. It is like stretching a rubber band, except this rubber band does not snap. It does something far stranger. When enough energy has accumulated in the color field between the separating quarks, something extraordinary happens. Something that has no parallel in electromagnetism, in gravity, in any force you have ever experienced. The energy stored in the field becomes sufficient to create new particles. New quarks materialize from the concentrated energy, appearing where nothing existed a moment before. These new quarks instantly pair with the originals, forming new, color-neutral hadrons. You started trying to pull two quarks apart, and you ended up not with two free quarks, but with more particles than you began with. The quarks were never freed. They were reorganized into new prisons. This is what happens when you try to pull two quarks apart. And understanding the precise mechanism behind it, the way the color field narrows and concentrates between separating charges, the way energy accumulates and transforms into new matter, the way the system reorganizes itself to enforce color neutrality at every step of the process, is what we are about to explore. Now let's watch what actually happens. We have established that quarks carry color charge, that gluons transmit the strong interaction, and that those gluons, unlike photons, carry color charge themselves. We have seen that gluon self-interaction weakens the coupling at very short distances and strengthens it at larger ones. But so far, we have described these facts without truly following the color field itself, step by step, as two quarks are forced apart. And the behavior of that field is where the deepest strangeness of the strong interaction lives. To see it as clearly as possible, we need the simplest system available, not a proton. A proton contains three quarks bound together in a complicated three-way color arrangement. And the geometry of the color field inside it is far more complex than a single connection between two objects. Three quarks carrying three different color charges interact through multiple gluon exchanges simultaneously, producing a field structure that cannot be reduced to one simple tube linking two endpoints. Instead, let's use a meson. A meson is a hadron containing exactly two particles, one quark and one antiquark. The quark carries a color charge, say red. The antiquark carries the matching anti-color, anti-red. Together the pair is color neutral. The meson is the cleanest possible laboratory for understanding what happens when color charges separate, because you have exactly two charges with one color field stretching between them. Everything we are about to describe applies in a more complicated way inside baryons like protons and neutrons, but the essential physics, the concentration of field energy, its accumulation with distance, and its eventual conversion into new matter is most clearly illustrated in this quark-antiquark case. Now imagine you could reach in, grab the quark with one hand, and the antiquark with the other, and start pulling. What happens to the color field between them? Before we answer that, we need to look carefully at how a more familiar force behaves under the same conditions. Because the color field does something so radically different from everyday experience that you need a clear point of comparison to appreciate it. And the best comparison is electromagnetism. Take two electrically charged particles, a positive charge and a negative charge, sitting close together. Between them exists an electric field. You can picture this field as a collection of field lines, invisible threads of influence reaching from one charge to the other, representing the direction and strength of the force at every point in space. When the charges sit close, the field lines are concentrated between them. The field is strong. The force is significant. Now start pulling the charges apart. As the distance grows, something important happens. The field lines spread outward. They fan into the surrounding space like the ribs of an opening umbrella. The field energy, which was concentrated in a small region when the charges were close, now disperses across a larger and larger volume. As the energy dilutes, the force drops. Double the distance, 1/4 the force. Triple it, 1/9. This is the familiar inverse square law. Triple it and the force drops to 1/9. The electromagnetic force fades smoothly and predictably because photons, the carriers of that force, do not interact with each other. A photon flying between two charges travels in a straight line, unaffected by other photons. Nothing constrains the field lines to stay close together. They are free to radiate outward in all three dimensions, and the energy thins across an ever-expanding sphere. This geometric spreading is precisely why the force follows an inverse square law. It is a straightforward consequence of non-interacting force carriers in three-dimensional space. The practical consequence is decisive. Because the electromagnetic force weakens with distance, it can always be overcome. Supply enough energy and you pull an electron completely away from a proton. The energy required is finite. Ionization, stripping electrons from atoms, happens constantly throughout the universe. Every neon sign, every lightning bolt, every star depends on it. Electromagnetic binding is real, but it has a finite price. Pay that price and the charges go free. Now, erase that picture from your mind, because what happens between two color charges is entirely different. When a quark and an antiquark sit close together inside a meson, a color field exists between them. At very short distances, this field actually looks somewhat similar to an electromagnetic field, roughly spread out and following a pattern that resembles the familiar inverse relationship. This is the regime of asymptotic freedom. The coupling is weak, the gluon self-interactions have not yet asserted themselves, and the theory behaves in ways that are not too far from electromagnetism. But as you begin to pull the quark and antiquark apart, the color field does not spread outward. The field lines do not fan into the surrounding space. They do the opposite. They squeeze inward. This is a direct consequence of gluon self-interaction. When the color field attempts to spread, the gluons in that field interact with one another, pulling the field lines back inward, compressing them, concentrating them into a progressively narrower region between the two separating charges. In electromagnetism, the field spreads freely and the energy dilutes over a larger volume. In quantum chromodynamics, gluon self-interactions prevent the field from spreading. The energy stays concentrated, and as you continue pulling the quark and antiquark farther apart, the color field between them becomes squeezed into a long, narrow tube of concentrated field energy. This structure has a name. Physicists call it a flux tube, sometimes a color flux tube or a chromoelectric flux tube. It is a tube-shaped region of intense color field energy connecting the separating quark and antiquark. The field lines run parallel inside this tube, compressed together by gluon self-interactions, forming a tight bundle of color force that stretches between the two charges. The flux tube has a characteristic width of roughly 1 femtometer, approximately the diameter of a proton. Outside this narrow region, the color field drops to essentially zero. All the energy of the interaction is concentrated inside the tube. None of it leaks into the surrounding space. To appreciate how alien this behavior truly is, try to picture it unfolding in slow motion. Imagine you could somehow watch the color field evolve as the quark and antiquark begin their separation. At first, when the charges sit close together, the field fills the space around them in a roughly symmetrical cloud. Energy is distributed through a volume of space surrounding the two charges. It looks, in a loose sense, like what you might expect from any force field. It resembles the electromagnetic picture, familiar, intuitive, unremarkable. But as the separation grows, something begins to change. The outermost reaches of the field, the regions farthest from the line connecting the two charges, start to pull inward. The field lines that were reaching into the surrounding space curve back toward the central axis. It is as though the field is being gathered by invisible hands, folded back upon itself, drawn in from every direction. The gluons in the field are interacting with one another, tugging on each other, and their collective effect is to compress the field toward the center line between the charges. Within a remarkably short distance of separation, the transformation is complete. What was a diffuse, three-dimensional cloud has become a tight, narrow column. All the field energy that once spread across a volume of surrounding space has been squeezed into an almost one-dimensional structure. Outside this slender corridor, space is essentially empty. No color field, no strong force, nothing. Every trace of the interaction between the two charges has been funneled into this bridge of concentrated gluon field running between them. If you could somehow make the color field visible, it would look like a luminous thread stretched taut between 2 points. It grows longer as the charges move apart, but it never grows wider. The width remains fixed at roughly 1 femtometer regardless of how far the charges separate. The tube could stretch to 10 femtometers, 100, 1,000 in principle, and it would still be approximately 1 femtometer across. The field refuses to spread. The gluons hold it together, pulling inward with the same relentless force that the tube exerts along its length. This is a cage that builds itself as you try to escape it. The flux tube is not a physical object in the ordinary sense. You cannot touch it, weigh it, or examine it under a microscope. It is a configuration of the quantum color field, a pattern that the gluon field organizes itself into when two color charges are pulled apart. But it is as real as any field configuration can be. It carries energy, it has a measurable width, and it has consequences that are dramatic and experimentally verifiable. At this point, a familiar analogy becomes very tempting. The flux tube behaves in some ways like a stretched elastic band or a taut string connecting two objects. As you pull the objects apart, the string stretches. The farther you pull, the more tension builds. This analogy captures something genuine. The energy stored in the flux tube does increase with separation, much as tension in an elastic band increases as you stretch it. But this analogy must be handled carefully. The flux tube is not a string. It is not an elastic band. It is not a cord made of some exotic material. It is a quantum field phenomenon. When physicists describe a string connecting quarks, they are describing the mathematical properties of the flux tube, not claiming there is a literal piece of thread inside every proton. The flux tube emerges from the equations of quantum chromodynamics. It is a prediction of the theory confirmed by computational simulations, and it shares certain mathematical behaviors with a classical string. But it is fundamentally a quantum object, subject to quantum fluctuations and effects that no physical string could exhibit. Keep this distinction in mind as we continue. With that caveat firmly in place, let us look at what the flux tube does as the separation between the quark and antiquark increases. And this is where the strong interaction diverges from electromagnetism in the most dramatic way possible. In electromagnetism, the potential energy between two opposite charges changes according to the inverse of the distance. Pull them apart and the energy rises, but it rises more and more slowly as the separation grows. The curve flattens. At infinite separation, the energy approaches a finite limit. This means that if you supply enough energy, finite energy, you can completely separate the charges. You can pull them apart and send them to opposite sides of the universe. The cost is real but bounded. The flux tube between color charges behaves in a fundamentally different way. As you pull the quark and antiquark apart, the tube stretches. But because the field lines are confined to the tube rather than spreading into space, the energy stored in the field does not level off. It does not approach a limit. Instead, the energy grows roughly in proportion to the separation distance. Double the distance between the quark and antiquark, and you roughly double the energy stored in the flux tube. Triple the distance, triple the energy. The relationship is approximately linear. Physicists characterize this behavior using a quantity called the string tension. It is a measure of how much energy is stored per unit length of the flux tube. The value, determined from both lattice simulations and experimental measurements, is approximately 1 giga-electron-volt per femtometer. This is an enormous energy density. 1 femtometer is 1 quadrillionth of a meter. In that minuscule distance, the flux tube stores roughly 1 giga-electron-volt of energy, which is comparable to the entire rest mass energy of a proton. Every additional femtometer of separation you try to impose between the quarks costs you another giga-electron-volt of field energy. Let me make this tangible. At a separation of about 1 femtometer, roughly the size of a proton, the effective force between the quark and antiquark is equivalent to about 14 metric tons. 14 metric tons of force between two objects, each vastly smaller than an atom. For comparison, the electromagnetic force holding the electron to the proton inside a hydrogen atom is roughly 2 trillion times weaker. The strong force earns its name. And here is the critical point. This force does not weaken as you pull farther. In fact, the force between two quarks connected by a flux tube remains approximately constant over a significant range of separations. Unlike gravity, unlike electromagnetism, unlike any other force in your experience, the color force mediated by the flux tube does not diminish with distance. You pull harder. The force does not budge. You pull harder still. The force stays the same. Every increment of separation costs you the same additional energy as the last. This creates a trap without an exit. In electromagnetism, you can always escape because the force weakens as you retreat. Eventually you reach a distance where the grip is negligible and you are free. With the color force, no such distance exists. The force remains constant. The energy cost keeps climbing. You never reach a point where the field lets go. This is why simply applying more force does not work. Supplying more energy does not accelerate one quark away from the other into freedom. That additional energy does not become the kinetic energy of an escaping quark. It is absorbed by the flux tube. It feeds into the color field, stored as field energy, trapped in that narrow cylinder of gluons, stretching between the separating charges. The more energy you supply, the longer and more energetic the flux tube becomes, but the quarks remain connected. The prison does not weaken. It grows. You might wonder how physicists actually know this. We cannot see a flux tube directly. We cannot photograph the color field inside a meson or insert a measuring instrument between two quarks. So how do we know the field squeezes into a tube, that the energy rises linearly, that the string tension has the value it does? The answer comes from one of the most remarkable achievements in computational physics. It is called lattice quantum chromodynamics, often shortened to lattice QCD. The central difficulty of quantum chromodynamics at confinement scale distances is that the standard mathematical tools of theoretical physics collapse. The technique called perturbation theory, which works brilliantly at high energies where the coupling is weak, fails completely when the coupling becomes strong. In the non-perturbative regime where confinement operates, you cannot treat the interaction as a small correction to anything. It is the dominant feature of the system. Pencil and paper methods cannot solve the equations. In 1974, the American physicist Kenneth Wilson proposed a radical approach. Instead of trying to solve the equations analytically, he suggested placing the entire theory on a discrete grid. He replaced continuous spacetime with a four-dimensional lattice of points, separated by a tiny spacing. Quarks were placed at the lattice sites. Gluon fields were represented by mathematical objects living on the links between sites. The full theory of quantum chromodynamics was reformulated on this grid in a way that becomes exactly equivalent to the continuous theory in the limit, where the lattice spacing shrinks to zero. The brilliance of this method was that once you have a discrete lattice, you can use a computer. You program the rules of quantum chromodynamics, place quarks on the lattice, and let the gluon field evolve according to the exact equations of the theory. No clever approximations, no perturbative shortcuts. The complete non-perturbative dynamics, including all gluon self-interactions, are handled directly by the simulation. Kenneth Wilson received the Nobel Prize in Physics in 1982 for his theory of critical phenomena in phase transitions, but his invention of lattice gauge theory proved equally transformative for particle physics. These simulations demand extraordinary computing power. The lattice must be fine enough that the spacing is much smaller than the physical distances being studied. It must also be large enough that boundary effects do not distort the results. And the quantum nature of the theory requires generating thousands or millions of random field configurations, weighted by their quantum probability and averaging over all of them using statistical sampling techniques called Monte Carlo methods. Modern lattice QCD calculations run on the largest supercomputers in the world for weeks or months at a time. To give you some sense of the scale involved, a typical modern lattice simulation might divide spacetime into a grid with something like 64 points along each of 4 dimensions. That is roughly 17 million lattice sites. At each site and on each link between sites, the gluon field is represented by mathematical objects that must be updated throughout the calculation. The total number of variables in a single field configuration can reach into the hundreds of millions. But one configuration is not enough. The quantum nature of the theory means that no single arrangement of gluon fields gives the correct answer. Instead, physicists must generate thousands or even tens of thousands of independent field configurations, each one representing a possible state of the vacuum, each one weighted by its quantum mechanical probability. The physical predictions emerge only as statistical averages over this vast ensemble. It is like trying to determine the temperature of a room by measuring the speeds of millions of individual air molecules and averaging the results. Any single measurement tells you almost nothing. The truth emerges only from the collective behavior of the whole ensemble. The computing resources required are staggering. A single state-of-the-art lattice calculation can consume tens of millions of processor hours. That is equivalent to one computer running continuously for thousands of years. In practice, the work is distributed across thousands of processors running in parallel on the most powerful machines available. These are calculations that would have been completely impossible when Kenneth Wilson first proposed the method. Only the exponential growth in computing power over the following decades made them feasible. Over the decades since Wilson's proposal, lattice QCD has matured into a precision science. Modern simulations include the effects of dynamical quarks and antiquarks appearing and disappearing in the vacuum. They produce predictions that match experimental measurements with remarkable accuracy, typically agreeing to within a few percent or better the masses of hadrons, the properties of the quark-gluon interaction, the decay rates of composite particles. All of these have been calculated from first principles on the lattice and confirmed by experiment. And what do lattice simulations reveal about the color field between a separating quark and antiquark? Exactly what we described. The field squeezes into a flux tube. Modern simulations produce detailed maps of the energy density between a static quark and antiquark on the lattice. At short separations, the field distribution looks somewhat like an electromagnetic dipole, spread out and roughly spherical. But as the separation increases, the field rapidly collapses into a narrow, elongated tube running between the two charges. The energy density outside the tube drops to nearly zero. Essentially, all the field energy is concentrated in this narrow cylinder. The simulations also confirm the linear rise of energy with distance. When physicists measure the potential energy between a quark and antiquark on the lattice as a function of their separation, they find two distinct regimes. At short distances, the potential resembles the familiar electromagnetic form, varying as the inverse of the separation. This is the domain of asymptotic freedom, where the coupling is weak. But at larger distances, the curve changes character. It stops flattening and becomes a straight line, climbing linearly with separation. The slope of that line is the string tension, and the value extracted from lattice simulations matches the value inferred from the experimental spectrum of hadron masses. The full potential, combining both regimes, is sometimes called the Cornell potential, after physicists at Cornell University who first proposed this combined form. At short range, the interaction looks electromagnetic. At long range, it looks like a string with constant tension. The crossover between the two regimes occurs at roughly the scale of a hadron, about 1 femtometer. This linear potential is the mathematical signature of confinement. If the energy required to separate two quarks grows without limit, rising in direct proportion to the distance, then no finite amount of energy can purchase their freedom. There is no ionization energy, no finite threshold beyond which the quarks break free. The cost of separation is unbounded. But here is where we must be precise. The statement that energy rises without limit as the flux tube stretches forever is not the complete physical picture. Something else happens before the energy reaches infinity. The tube does not stretch to infinite length and infinite energy. The universe does not permit that. At some critical separation, the energy stored in the tube becomes large enough that a qualitatively new physical process takes over. This process does not involve the tube simply snapping the way a physical rope might break, leaving two loose ends with free color charges dangling in space. What actually occurs is far stranger and far more beautiful than a simple mechanical failure. It is worth pausing here to acknowledge something important about the state of our knowledge. lattice QCD provides overwhelming numerical evidence for confinement. The simulations reproduce the flux tube, the linear potential, the string tension, and the spectrum of hadron masses with impressive accuracy. Experimentally, no isolated quark has ever been detected in any search ever conducted, at any energy, in any environment. The evidence is total. Nobody seriously doubts that confinement is real. It is one of the most solidly established facts in all of particle physics. But proving confinement analytically, deriving it rigorously from the mathematical axioms of quantum chromodynamics, using formal mathematics rather than numerical simulation, has never been accomplished. This is not a minor technical gap. It is considered one of the most important unsolved problems in theoretical physics and mathematics. The Clay Mathematics Institute has listed it among its 7 Millennium Prize problems, offering a $1 million prize for a rigorous proof that Yang-Mills gauge theories, the class of theories to which quantum chromodynamics belongs, exhibit a property called a mass gap. The mass gap is intimately connected to confinement. If the theory possesses a mass gap, it means the lightest physical particle it produces has a non-zero mass, which implies that the color force does not propagate freely over long distances the way electromagnetism does. Proving the existence of this mass gap from first principles would be a monumental mathematical achievement, on par with the greatest theorems in the history of the discipline. As of today, no one has succeeded. This situation is humbling and revealing in equal measure. We possess a theory that agrees with every experiment ever performed. It predicts hundreds of measured quantities correctly, often to extraordinary precision. In the high-energy regime, perturbation theory yields some of the most accurate predictions in all of science. In the low-energy regime, lattice simulations confirm its predictions with great accuracy. Yet, a complete, rigorous, pen and paper derivation that confinement follows inevitably from the theory's own equations has not been produced. We believe it does. Every scrap of evidence says it does, but the mathematical proof remains beyond our current capabilities. This does not cast doubt on confinement. It reveals that our mathematical tools are not yet powerful enough to extract everything the theory contains. The very properties that make quantum chromodynamics capable of confining quarks, the strong coupling, the gluon self-interactions, the non-perturbative dynamics, are the same properties that resist analytical proof. The force that traps quarks also traps our equations. The difficulty of the proof is itself a reflection of how extraordinary the physics truly is. So here is where we stand. A quark and an antiquark are being pulled apart. Between them, the color field has collapsed into a narrow flux tube, a concentrated cylinder of gluon field energy running from one color charge to the other. The energy stored in this tube grows linearly with separation. The force does not weaken. The quarks do not approach freedom. Every unit of additional distance costs the same increment of energy as the one before. The flux tube absorbs everything you throw at it, but the flux tube cannot stretch forever. At some point, enough energy accumulates inside it to cross a critical threshold, and when that threshold is reached, something happens that overturns every intuition you have ever developed about pulling things apart. The energy stored in the color field between those two quarks does not simply dissipate. It does not leak away. It does something that changes the particle content of the universe. New matter is created from the energy of the field itself. And what emerges is not freedom for the original quarks, but an entirely new set of prisoners. We left off staring at a flux tube under unbearable tension. a quark and an antiquark, being pulled apart with a narrow cylinder of concentrated color field energy stretching between them. Energy rising linearly with every increment of separation. No sign of weakening, no sign of relief. The system looks like it could stretch forever, accumulating more and more energy in that tube without limit. But the universe does not permit infinite tension in a flux tube any more than it permits isolated color charges. Something gives, and what gives is not the tube. What gives is the vacuum itself. To understand what happens next, you need to appreciate something about empty space that is deeply counterintuitive. The vacuum, the space that appears to be absolutely nothing, is not actually empty. In quantum field theory, the vacuum is seething with activity. It is filled with what physicists call quantum fluctuations, temporary disturbances in every quantum field that permeate the universe. These fluctuations constantly produce pairs of particles and antiparticles that wink into existence for an unimaginably brief moment and then annihilate each other, vanishing back into the vacuum. These are called virtual pairs. They exist on borrowed energy for borrowed time, permitted by the uncertainty principle of quantum mechanics. Under normal circumstances, these virtual pairs have no lasting effect. They appear and disappear so quickly that they cannot be directly observed as free particles. They are ghosts that haunt the vacuum, leaving subtle traces but never fully materializing. But inside a flux tube stretched to its breaking point, circumstances are not normal. The field energy density inside the tube is enormous. The color field is intense, concentrated, and unstable. And when enough energy accumulates in the flux tube, the field provides exactly the energy needed for a virtual quark-antiquark pair to become real. Not a ghost that appears and vanishes. A real, permanent, physical pair of particles that spring into existence and remain. This is not a metaphor. It is a physical process predicted by quantum chromodynamics, confirmed by lattice simulations, and consistent with every experimental observation of hadron production ever made. The concentrated energy in the color field between the separating quark and antiquark becomes sufficient to produce a new quark and a new antiquark from the vacuum. Let me be absolutely clear about where the energy comes from, because this is a point that is often misunderstood. The new particles do not appear from nothing. They do not violate any conservation law. The energy required to create them, to supply their rest mass and their kinetic energy, comes directly from the energy stored in the flux tube. And the energy stored in the flux tube came from the work you did in pulling the original quark and antiquark apart. You supplied energy by forcing the color charges to separate. That energy was absorbed by the color field. The field stored it in the flux tube. And now the field converts that stored energy into the mass and motion of new particles. This is Einstein's equivalence of mass and energy at work. E equals mc squared. Energy and mass are interchangeable. A concentration of energy in a field can become a concentration of mass in a particle. The total energy of the system is conserved at every step. Nothing is created from nothing. The energy budget balances perfectly. You started by pumping energy into the system by pulling the quarks apart. That energy was stored in the flux tube. And now that stored energy has been converted into matter. The moment this pair creation occurs, something beautiful and precise happens. The newly created quark does not fly off by itself. The newly created antiquark does not escape into freedom. Remember, no color charge is ever permitted to exist in isolation. The universe enforces color neutrality at every moment. So the new quark, which carries its own color charge, immediately pairs with one of the original particles, and the new antiquark pairs with the other. Specifically, the newly created antiquark finds the original quark and forms a new color-neutral pair with it. The newly created quark finds the original antiquark and forms a new color-neutral pair with it. The result is two separate mesons where there was originally one. You start with one quark and one antiquark bound together in a single color-neutral meson. You tried to pull them apart. You pumped energy into the color field between them. That energy stretched the flux tube. And when the tube reached a critical energy, it produced a new quark-antiquark pair that reorganized the system into two separate color-neutral mesons. Neither of the original quarks is free. Neither of the new quarks is free. Every single quark in the final state is locked inside a hadron. Confinement has been maintained at every step of the process. The color field broke, but it broke in the only way the universe allows. Not by releasing bare color charges, but by creating new partners to ensure that every color charge is always matched and neutralized. This process is called string breaking. The name comes from the string-like behavior of the flux tube. You stretched the string until it reached a critical tension. Then it broke. But the breaking did not produce two loose ends with bare color charges hanging free. The breaking produced two new endpoints, one quark and one antiquark, that immediately capped the broken ends. Each fragment of the original string became a complete, color-neutral hadron. Now here is something crucial to appreciate. The process does not stop at one pair. If you are supplying energy continuously, if the original quarks are still being driven apart with tremendous force, the newly created mesons can themselves be stretched. Their internal quarks can be pulled apart by the residual momentum and energy in the system. And if enough energy is available, the same thing happens again. Another flux tube stretches, another pair is created, another set of hadrons is produced. In principle, this process can repeat many times, each time converting available energy into new quark-antiquark pairs and new hadrons. This is exactly what happens in high-energy particle collisions. And understanding this cascade of pair creation and hadron formation is essential to understanding how modern particle physics actually observes and studies quarks, despite the fact that no quark has ever been seen in isolation. Let's move from the idealized picture of gently pulling two quarks apart and step into the real world of experimental particle physics. Because in a particle accelerator, quarks are not pulled apart slowly and carefully. They are blasted apart with staggering violence. The energies involved are so enormous that the process of pair creation and hadron formation plays out in a spectacular, rapid, and intricate cascade. And the result is one of the most striking phenomena in all of experimental physics: the particle jet. Consider what happens at a particle collider, like the Large Hadron Collider at CERN. Two protons are accelerated to nearly the speed of light, and then steered into a head-on collision. The total collision energy can exceed 13,000 giga-electron volts, more than 13,000 times the rest mass energy of a single proton. At these energies, the collision does not simply bounce the protons off each other. It probes deep inside them. The individual quarks and gluons inside the colliding protons interact directly at extremely short distances. In a typical high-energy collision, one quark inside one proton strikes a quark or gluon inside the other proton. At the moment of impact, the interaction occurs at such a short distance that asymptotic freedom applies. The quarks are nearly free. The collision scatters them at enormous energies, sending them flying apart at close to the speed of light. But the scattered quark cannot simply fly away from the collision point and be detected as an isolated particle. It carries color charge, and the moment it begins to separate from the other color charges it was bound with, the color field between them begins to stretch. A flux tube forms, energy accumulates, and within an extraordinarily short time, the tube reaches the threshold for pair creation. At the energies available in a modern collider, this process does not happen just once. It happens many, many times in rapid succession. The outgoing quark, carrying enormous kinetic energy, drags a flux tube behind it. The tube breaks, creating a new quark-antiquark pair. The new quark pairs with the remnant left behind. The new antiquark continues forward with the original quark, forming a new meson that itself carries considerable energy. But the original quark is still moving at tremendous speed, and another flux tube immediately forms between it and its new partner. That tube breaks too. More pairs are created. More hadrons form. Each breaking produces new particles that carry a share of the original quark's momentum. This cascade is called hadronization. The original quark's color charge is never exposed. Instead, it is converted through repeated pair creation into a spray of color-neutral hadrons, pions, kaons, protons, and many other composite particles, all flying forward in roughly the same direction as the original quark. This narrow, concentrated spray of hadrons is what physicists call a jet. A jet is not a stream of quarks. It is a stream of hadrons, dozens or hundreds of composite particles, all produced by hadronization, all flying in approximately the same direction, carrying a collective share of the original quark's energy and momentum. When a high-energy quark is produced in a collision, what the detector actually sees is a jet. A tight bundle of hadrons all moving in the same direction, depositing their energy in the detector in a characteristic cone-shaped pattern. The existence of jets is itself powerful evidence for quarks. If protons were truly structureless, featureless blobs of matter, you would not expect to see tightly collimated sprays of particles emerging from collisions. The jets reflect the fact that a point-like object carrying enormous momentum was produced in the collision and then fragmented into many hadrons through the process of pair creation and color field breaking. The direction and energy of the jet correspond to the direction and energy of the original quark. Gluons produce jets too. When a gluon is knocked out of a proton during a collision, it undergoes the same hadronization process. The gluon carries color charge, so a flux tube forms. The tube breaks, pairs are created, hadrons are produced. The result is another jet, pointing in the direction the gluon was heading. In fact, one of the landmark discoveries in particle physics was the observation of 3 jet events in electron-positron collisions at the Petra Accelerator in Hamburg in 1979. 2 of the jets corresponded to the outgoing quark and antiquark. The 3rd jet corresponded to a hard gluon radiated by one of the quarks before hadronization. This was among the first direct experimental evidence for the physical existence of gluons as real particles, not just mathematical abstractions. You might wonder how physicists can study the properties of quarks and gluons if they can never isolate them. If every quark immediately hadronizes into a jet of composite particles, how do we know anything about the quark itself? The answer is that the jet preserves information about the original quark or gluon. The total energy and momentum of the jet match those of the original quark. The direction of the jet points back to where the quark was heading when it was produced. Imagine someone fires a cannonball through a wall of thin glass. It shatters on impact, producing hundreds of glass fragments that spray forward in a cone. You never see the cannonball itself because it was destroyed in the collision with the glass. But by collecting all the fragments, measuring their speeds and directions, and adding up their masses and momenta, you can reconstruct the energy, direction, and speed of the original cannonball with remarkable precision. The fragments tell you everything about the projectile that created them. That is essentially what particle physicists do with jets. The hadrons in the jet are the fragments. By measuring each hadron's energy and momentum using sophisticated detectors surrounding the collision point, physicists reconstruct the properties of the original quark or gluon. They can determine its energy, its direction, its flavor, and even subtle properties like whether it was a quark or a gluon based on the detailed structure of the jet. This reconstruction is so precise that physicists routinely talk about producing quarks and gluons in collisions. They refer to the top quark being produced, or a bottom quark being struck, or a pair of gluons fusing together. This language can create a misleading impression if you are not familiar with the physics behind it. It sounds as though quarks and gluons are being produced as free particles, flying across a detector and being captured. They are not. What is actually produced is a jet. What is actually detected is a collection of hadrons. The quark is inferred, reconstructed, and measured through its fragmentary footprint in the detector. The quark itself was never free. It was confined at every instant, from the moment of its creation to its hadronization into the observed jet. Let me describe the process in slightly more detail, because the physics of hadronization is richer than a single pair creation event. When a quark is produced with very high energy, the first thing that happens is not immediately hadronization. There is an intermediate phase called parton radiation. A parton is a generic term for any constituent of a hadron, quarks and gluons alike. A high-energy quark, while still carrying its enormous kinetic energy, can radiate gluons, much as a charged particle radiating photons in electromagnetism. These radiated gluons themselves carry color charge and can radiate further gluons or split into quark-antiquark pairs. The result is a shower of partons, quarks, and gluons, all moving roughly in the same direction as the original quark and sharing its total energy among themselves. This parton shower develops over an extremely short time. It begins at the highest energy scales, where asymptotic freedom holds and the coupling is weak enough for the radiation to be calculated using perturbation theory. Each successive splitting produces partons with lower energy. As the energy of individual partons decreases, the coupling grows stronger. Eventually, the individual partons reach energies where the strong coupling becomes large and the non-perturbative regime takes over. At this point, perturbation theory can no longer describe what happens. The partons are now at energy scales where confinement dominates. This is where hadronization occurs. The partons, each carrying color charge, organize themselves into color-neutral hadrons. Flux tubes form between color-connected partons. Those tubes break through pair creation. New quarks and antiquarks partner with the existing partons. And within an incredibly short time, the parton shower has transformed entirely into a collection of hadrons. The whole process, from the initial hard collision to the final hadron production takes roughly 10 trillionths of a trillionth of a second. The exact mechanism of hadronization is one of the areas where theoretical understanding is most difficult. Because hadronization occurs in the non-perturbative regime, it cannot be calculated from first principles using standard analytical methods. Physicists rely on phenomenological models, mathematical frameworks calibrated to match experimental data, to describe how partons convert into hadrons. Two of the most successful models are the string fragmentation model and the cluster hadronization model. Both capture the essential physics of color field breaking and pair creation through different mathematical approaches. The string fragmentation model, developed primarily at Lund University in Sweden, treats the color field between partons as a relativistic string with a constant string tension. As the partons separate, the string stretches, accumulates energy, and breaks through pair creation at various points along its length. Each break produces a new quark-antiquark pair. Adjacent quarks and antiquarks pair up to form mesons or baryons. The model successfully reproduces the distributions of hadrons observed in experiments with impressive accuracy. The cluster hadronization model, used in several modern simulation programs, takes a different approach. After the parton shower, it groups color-connected quarks and gluons into clusters, compact regions of color-neutral matter. These clusters then decay into the observed hadrons. The two models use different intermediate descriptions but converge on the same observable predictions, which gives physicists confidence that the essential physics, color confinement through pair creation, is captured regardless of the specific modeling details. What matters for our story is the final result. In every high-energy collision where quarks or gluons are produced, the outcome is always the same. Not free quarks, not isolated gluons, jets of hadrons. The process of hadronization is universal and inescapable. It occurs every single time a color-charged particle is produced at any energy. The details vary. The number of hadrons in a jet depends on the energy available. A low-energy quark might produce only a handful of pions. A high-energy quark at the Large Hadron Collider might produce dozens or hundreds of hadrons in a single jet. But the principle is identical in every case. Color charges must be neutralized. Pair creation accomplishes this, and hadrons are the inevitable result. This brings us to a point that deserves emphasis because it addresses a common source of confusion. How can physicists describe quarks as being struck or produced in collisions if quarks are permanently confined? Does this not contradict confinement? No, it does not. And the resolution lies in understanding the difference between what happens at short distances and what happens at long distances. At the instant of a high-energy collision, the interaction between the incoming particle and the quark inside a proton takes place at an extremely short distance. At that distance, asymptotic freedom applies. The quark behaves almost as though it were free. The strong coupling is weak. The quark absorbs the energy of the collision and recoils just as a free, point-like particle would. Every measurement of this initial interaction, the scattering angle, the energy transfer, the probability of the collision occurring, matches the predictions of a theory in which the quark is essentially free at the moment of impact. But the quark is not free in the long-distance sense. After the initial collision, as the struck quark begins to separate from the remnants of the proton it was inside, the long-distance physics takes over. The coupling grows, the flux tube forms, Pair creation begins, hadronization follows. The quark never reaches the detector as a free particle. So the statement that a quark was struck in a collision is true in the short distance sense. At the moment of impact, the quark behaved as a nearly free, point-like object. And the statement that the quark was confined is also true in the long-distance sense. The quark never escaped as an isolated particle. Both descriptions apply. They describe different distance scales of the same process. The transition between them from the perturbative world of asymptotic freedom to the non-perturbative world of confinement is the heart of hadronization. This is why deep inelastic scattering experiments, the experiments that first revealed quarks inside protons in the late 1960s and early 1970s, did not contradict confinement. Those experiments fired high-energy electrons at protons. The electrons scattered off the quarks inside the proton, and the scattering patterns were exactly what you would expect from point-like, nearly free objects. This was some of the first evidence that quarks were real physical entities. But the quarks revealed by those scattering patterns never emerged from the proton as free particles. They remained confined. The experiment probed the short-distance structure of the proton and found quarks there, but the quarks stayed inside. The same principle applies at every modern collider. At the LHC, when physicists announce the production of a top quark, what they actually detect is a specific pattern of hadrons and other particles in the detector. The top quark is inferred from that pattern, reconstructed from the energies and momenta of its decay products. No one has ever seen a free top quark sitting in a detector. What they see is its fingerprint, an unmistakable signature that could only have been produced by the creation and immediate decay of a top quark. The top quark existed. It was real, but it was never free. It decayed so rapidly, within roughly 5 × 10 to the negative 25 seconds, that it did not even have time to hadronize. It decayed into other particles before a flux tube could fully form. But those decay products, a bottom quark and a W boson, themselves undergo hadronization or further decay, and the final state observed in the detector consists entirely of color-neutral particles. There is something profound in all of this. Every particle physics experiment ever conducted, every collision ever analyzed, every jet ever measured, tells the same story. Quarks are real. They exist inside protons, neutrons, and other hadrons. At short distances, they behave almost like free particles, but they are never ever observed as free, isolated objects. Every quark ever produced at any energy immediately becomes part of a new hadron through the process of pair creation and hadronization. The confinement is total. It is not approximate. It is not a tendency. It is absolute. And the mechanism that enforces it is exactly the process we have been describing. The color field between separating charges squeezes into a flux tube. Energy accumulates linearly with separation. When enough energy builds up, new quark-antiquark pairs materialize from that energy. The new quarks partner with the originals and form new color-neutral hadrons. At every stage, color neutrality is maintained. No bare color charge is ever exposed. The universe reorganizes its particle content rather than allowing a single quark to go free. What enters the detector is never a quark. It is always a collection of hadrons that preserves the quark's energy, momentum, and essential identity as surely as a footprint preserves the shape of the foot that made it. We reconstruct the quark from its traces. We measure its properties from its remnants. We know it was there because nothing else could have produced the pattern we observe. But the quark itself, naked and unconfined, remains forever beyond our direct reach. Confinement does not prevent us from studying quarks. It simply ensures that every observation is indirect, filtered through the unavoidable process of hadronization. We see the consequences of quarks, never the quarks themselves. And this is the answer to what happens when color charges are blasted apart in the most violent collisions humanity can engineer. The same thing that happens when they are gently pulled apart in the idealized thought experiment. The same thing that happens at every energy scale ever probed. Pair creation, hadronization, new prisons built from the energy that was meant to secure freedom. The universe does not negotiate on this point. Color charges remain confined, always. We have followed the color field from its first formation between two separating quarks, through the squeezing of that field into a flux tube, through the accumulation of energy, and through the moment of pair creation that breaks the tube and produces new hadrons. Every step enforces the same rule. Color charges are never permitted to exist in isolation. The universe always reorganizes its particle content to ensure that every quark is locked inside a color-neutral hadron. But there is a question that this picture naturally raises, and it is a question that causes enormous confusion if it is not addressed carefully. You have almost certainly heard of the strong force before, possibly in the context of what holds atomic nuclei together. You may have been taught in school that the strong force is the force that keeps protons and neutrons bound inside the nucleus of an atom. And that statement is not wrong, but it is deeply incomplete. And the incompleteness creates a misunderstanding so common that even many people with a serious interest in physics carry it without realizing. There are not two separate strong forces. There is one. Quantum chromodynamics describes a single fundamental interaction. But that interaction manifests at two very different scales in two very different ways. And failing to distinguish them leads to confusion about what confinement actually means. At the deepest level, the strong interaction operates between quarks and gluons through color charge. This is the interaction we have been describing throughout this entire journey. Quarks carry color. Gluons transmit the force and carry color themselves. Gluon self-interactions squeeze the field into flux tubes. The energy rises linearly with separation. Pair creation breaks the tube. Quarks are confined. This is the fundamental strong interaction. It is the force of quantum chromodynamics, and it operates inside individual hadrons, binding the quarks together so tightly that they can never escape. But protons and neutrons, the hadrons built from confined quarks, are themselves color neutral. A proton has 3 quarks, one red, one green, one blue, producing 0 net color charge. The same is true for neutrons. So when a proton sits next to a neutron inside an atomic nucleus, there should be no direct color force between them. They are both colorless. The fundamental strong interaction between color charges should not apply. And yet, protons and neutrons do bind together inside nuclei. Atomic nuclei exist. Iron, carbon, oxygen, gold, all the elements heavier than hydrogen, have nuclei containing multiple protons and neutrons held together by some attractive force. If the fundamental color force does not reach between color-neutral hadrons, what holds the nucleus together? The answer is the residual strong force, sometimes called the nuclear force. It is not the fundamental color interaction, but a secondary effect. a shadow of the much more powerful interaction happening inside the hadrons themselves. Here is the analogy that makes this clearest. Consider two electrically neutral atoms sitting near each other. Each atom has an equal number of protons and electrons. The net electric charge of each atom is 0. You might expect there to be no electromagnetic force between them. And at large distances, that is essentially correct. Two neutral atoms far apart exert almost no electromagnetic force on each other. But at very short range, things change. When two neutral atoms are close enough, the individual charges inside each atom can sense the individual charges inside the other. The positive nucleus of one atom is slightly attracted to the electron cloud of the other. The electron cloud of one atom is slightly repelled by the electron cloud of the other. These partial attractions and repulsions do not cancel perfectly at very close range. A small residual force remains. The van der Waals force, much weaker than the fundamental electromagnetic interaction between bare charges. It is a weak, short-range leftover of the underlying electromagnetic force, operating between objects that are individually neutral. The residual strong force works in exactly the same way, but with color charge instead of electric charge. A proton is color neutral overall, but at very short distances the individual quarks and gluons inside the proton can interact with the individual quarks and gluons inside a nearby neutron. The color charges do not cancel perfectly at close range. A residual attractive force emerges. This force is strong enough to bind protons and neutrons into nuclei, and it is responsible for nuclear physics, for nuclear energy, and for the existence of every element heavier than hydrogen. But this residual force is fundamentally different from the confinement mechanism. The residual nuclear force is a short-range, relatively weak leftover of the color interaction, operating between color-neutral hadrons. Confinement is the underlying color interaction itself, operating between individual quarks and gluons, preventing them from existing outside hadrons. The distinction matters enormously. The residual nuclear force can be overcome. You can split a nucleus. Nuclear fission does exactly this. You can supply enough energy to overcome the residual binding between protons and neutrons, and break a nucleus apart into smaller pieces. When you split a uranium nucleus, you are overcoming the residual strong force. And what you get is two smaller nuclei, each still made of protons and neutrons, each still containing confined quarks. But you cannot overcome confinement in the same way. You cannot split a proton the way you split a nucleus. If you supply enough energy to a proton, you do not get free quarks. You get new hadrons. The confinement mechanism does not weaken with additional energy. It converts that energy into new particles. The residual force and the confinement mechanism are different phenomena arising from the same underlying theory, but operating at different scales and with fundamentally different characters. In 1935, the Japanese physicist Hideki Yukawa proposed the first theoretical model of the nuclear force. He predicted that the force between protons and neutrons was carried by a new particle with a mass intermediate between the electron and the proton. This particle, later called the pion, was discovered experimentally in 1947. The pion is a meson, a quark-antiquark pair. In the modern understanding, the residual nuclear force between protons and neutrons is mediated primarily by the exchange of pions and other mesons between the hadrons. One hadron temporarily emits a meson, the other absorbs it, and this exchange generates an attractive force. The range of this force is limited by the mass of the exchanged meson. Heavier exchange particles produce shorter range forces. The pion, being the lightest meson, produces a force with a range of roughly 1 to 2 femtometers. Beyond this distance, the nuclear force drops to essentially zero. This is why nuclei have a definite size. The force simply does not reach far enough to bind protons and neutrons that are more than a couple of femtometers apart. Compare this to confinement. The color flux tube between quarks does not weaken at a range of a few femtometers. The energy keeps rising linearly. There is no distance at which the confinement mechanism fades away. The residual nuclear force has a finite range. Confinement has no upper range. These are qualitatively different phenomena, even though they both originate from the same fundamental theory of quantum chromodynamics. Understanding this distinction clears up one of the most persistent confusions in popular treatments of particle physics. When people say the strong force holds the nucleus together, they're talking about the residual force. When people say the strong force confines quarks inside protons, they are talking about the fundamental color interaction. The two statements describe different physical processes at different scales. The residual nuclear force is to the fundamental color interaction roughly what the van der Waals force is to the electromagnetic interaction. A weak, short-range shadow of something far more powerful happening at a deeper level. Now let's turn to something that may be the most remarkable consequence of confinement. Something that touches every atom in your body, every object you have ever held, every structure you have ever seen. It concerns the origin of mass itself. You probably think of mass as an intrinsic property of matter. An atom has mass because the particles inside it have mass. A proton has mass because the quarks inside it have mass. This seems obvious. It seems like basic arithmetic. Add up the masses of the parts and you get the mass of the whole. But this intuition, as natural as it feels, is almost entirely wrong. A proton has a mass of about 938 mega-electron volts. That number has been measured with extraordinary precision. It is one of the best known quantities in all of physics. Now let's look at what is inside the proton. 2 up quarks and 1 down quark. The mass of an up quark is approximately 2.2 mega-electron volts. The mass of a down quark is approximately 4.7 mega-electron volts. Add them up. 2 up quarks contribute about 4.4 mega-electron volts. 1 down quark contributes about 4.7. The total rest mass of the 3 quarks inside a proton is roughly 9.1 mega-electron volts. 9.1 mega-electron volts out of 938. The quarks account for less than 1% of the proton's total mass. Not 90%, not 50%, not even 10%, less than 1%. Over 99% of the mass of a proton does not come from the masses of the quarks inside it. It comes from something else entirely. Where does the rest of the mass come from? It comes from energy. Specifically, it comes from the energy of the quark and gluon system confined inside the proton. The quarks inside a proton are not sitting still. They are in constant, violent motion, rattling around inside their tiny prison at speeds that are a significant fraction of the speed of light. This motion gives them kinetic energy, and that kinetic energy contributes to the mass of the proton through the equivalence of mass and energy. But the kinetic energy of the quarks is only part of the story. The gluon field inside the proton is also enormously energetic. Gluons are constantly being emitted, absorbed, and exchanged between the quarks. They are splitting into temporary quark-antiquark pairs. They are interacting with themselves. The entire interior of the proton is a seething storm of gluon field activity. This gluon field carries an enormous amount of energy, and all of that energy, the kinetic energy of the quarks, plus the energy of the gluon field, contributes to the mass of the proton through Einstein's mass-energy equivalence. E equals mc squared tells us that energy and mass are two expressions of the same thing. A system that contains energy behaves as though it has mass. The proton is a confined system of quarks and gluons with enormous internal energy. That internal energy is what gives the proton its mass. The quarks themselves, their intrinsic rest masses, contribute almost nothing. This has a staggering implication. You are made of atoms. Atoms are made of protons, neutrons, and electrons. The electron mass is tiny, only about half a mega electron volt. The mass of any atom comes overwhelmingly from its protons and neutrons. And the mass of each proton and neutron comes overwhelmingly not from the quarks inside it, but from the energy of the confined quark and gluon system. This means that roughly 99% of the mass of everything you see around you, your body, the ground beneath your feet, the air you breathe, the planet you live on, does not come from the intrinsic masses of any fundamental particle. It comes from energy, from the kinetic energy of quarks and the energy of gluon fields, all of it trapped inside protons and neutrons by the mechanism of color confinement. You are, in the most literal physical sense, made almost entirely of energy, not in some vague metaphysical way, in a precise, measurable, quantitative way. The mass on your bathroom scale is overwhelmingly the energy of confined color fields and fast-moving quarks inside the protons and neutrons of your atoms. If confinement did not exist, if quarks could fly free and the gluon field could dissipate, that mass would vanish. The energy would disperse. You would cease to exist, not because your atoms fell apart, but because the mass that held those atoms together was never really mass in the traditional sense. It was confined energy. This fact has been confirmed with impressive precision by lattice QCD calculations. When physicists simulate a proton on the lattice, placing quarks and gluon fields on a discrete grid and letting the equations of quantum chromodynamics evolve, they can calculate the proton's mass from first principles. These calculations, which have been refined over decades and now include all the relevant physical effects, produce a proton mass that matches the experimentally measured value to within about 1%. And the calculation makes clear where the mass comes from. It does not come from the quark masses. It comes from the dynamics of the confined quark and gluon system, from kinetic energy and gluon field energy trapped by confinement. Let me slow down and make sure the enormity of this sinks in, because it is easy to hear a fact like this, nod along, and keep listening without truly absorbing what it means. So let's approach it from a different direction. Pick up any object near you right now. A pen, a cup, your phone. Feel its weight in your hand. That sensation of heaviness, that downward pull, is gravity acting on the object's mass. And almost all of that mass, over 99% of it, is not the intrinsic mass of any fundamental particle. It is energy. Trapped energy. Energy that has been locked inside protons and neutrons since those particles formed in the first moments after the Big Bang. And that has remained confined ever since. When you step on a bathroom scale and it reads, say, 70 kilograms, what you are really measuring is overwhelmingly the energy of color fields and fast-moving quarks imprisoned inside the protons and neutrons of your atoms. If you could somehow add up the intrinsic rest masses of every quark inside your body and ignore everything else, the scale would read less than 700 grams. Less than the weight of a small bottle of water. The remaining 69.3 kilograms is energy. Pure confined energy, given mass by Einstein's equivalence, held in place by the mechanism of confinement. Think about what this means for the world around you. The iron in a bridge, the stone in a mountain, the water in the ocean. The mass of every object you have ever encountered in your life is dominated by confined energy. When engineers calculate the load-bearing capacity of a steel beam, they are calculating how much confined energy that beam contains. When geologists measure the mass of the Earth, they are measuring the total confined energy of all the protons and neutrons in the planet. The entire material substance of the physical world, everything that has weight, everything that resists acceleration, everything that curves space-time and creates gravity, is overwhelmingly energy that quarks and gluons are unable to release because confinement will not let them. This also means that the mass of ordinary matter is not a fundamental quantity. It is an emergent one. It arises from the dynamics of confinement. The quark masses themselves are set by a completely different mechanism. The interaction of quarks with the Higgs field, which gives them their small intrinsic rest masses of a few mega-electron volts each. But that mechanism accounts for less than 1% of the mass of a proton. The remaining 99% comes from quantum chromodynamics, from the energy of confined color fields. The Higgs field gives quarks their seed masses. Confinement turns those seeds into the massive hadrons that make up the material world. Both mechanisms matter, but confinement is responsible for the vast majority of the mass you experience every day. Without the Higgs mechanism, quarks would be massless. Without confinement, protons would have no substantial mass even if the quarks did. Both mechanisms are necessary. But in terms of sheer contribution to the mass of the visible universe, confinement dominates overwhelmingly. It is not a subtle effect or a minor correction. It is the primary architect of the material world. The next time someone tells you that the Higgs boson is the origin of mass, remember that this is only partially true. The Higgs field gives fundamental particles like quarks and electrons their intrinsic rest masses. But the mass of ordinary composite matter, the mass of every proton and every neutron, the mass of your body and everything you can touch, is generated predominantly by confinement. This is one of the most profound results in all of modern physics. The mass of ordinary matter, the substance of everyday reality, the thing that gives objects weight and inertia, is not an intrinsic property of any fundamental particle. It is a consequence of confinement. A consequence of the fact that quarks and gluons are locked inside hadrons with enormous internal energy that cannot escape. Let me now address where our understanding stands, because it is important to be honest about what we know and what we do not. The physics of confinement is established beyond any reasonable doubt at the experimental level. No isolated quark has ever been observed. Jets of hadrons are produced in every high-energy collision, exactly as the confinement picture predicts. Lattice QCD calculations reproduce the hadron mass spectrum, the flux tube, the linear potential, and the string tension with a remarkable accuracy. Asymptotic freedom at short distances has been verified with some of the most precise measurements in all of science. The entire framework is consistent, predictive, and confirmed by decades of experiments at accelerators around the world. But a full analytical understanding of confinement a rigorous mathematical proof that quantum chromodynamics necessarily produces confinement, has not been achieved. The non-perturbative nature of the theory at confinement scale distances makes this extraordinarily difficult. The standard tools of theoretical physics, perturbation theory and Feynman diagrams, work brilliantly at high energies where the coupling is weak, but at the energies relevant to confinement, where the coupling is strong, these tools fail. The mathematics becomes intractable. We can simulate confinement on a computer. We can reproduce it numerically, but we cannot yet derive it on a blackboard in the way we can derive, say, the inverse square law of gravity from Newton's equations. This is why the Clay Mathematics Institute has listed the mass gap problem as one of its Millennium Prize problems. A rigorous proof that the theory confines would be a mathematical achievement of the highest order. There are also aspects of the confinement mechanism that remain subjects of active research. The precise structure of the color field inside a 3-quark baryon is more complicated than the simple flux tube we described for a quark-antiquark meson. Inside a proton, 3 quarks carry 3 different color charges. The field configuration connecting them is not simply 3 separate tubes meeting at a point. It may involve a more complex geometry, sometimes modeled as a Y-shaped junction, sometimes as a triangular arrangement. Lattice simulations have shed light on this, but the detailed dynamics remain an active area of study. The relationship between confinement and another non-perturbative phenomenon called chiral symmetry breaking is also an area of ongoing research. Chiral symmetry breaking is the mechanism by which quarks acquire their small but non-zero effective masses inside hadrons, and it is intimately connected to the dynamics of the gluon field. Understanding how confinement and chiral symmetry breaking relate to each other at a fundamental level is one of the frontier questions in theoretical particle physics. None of these open questions cast doubt on the reality of confinement. They indicate that we have not yet extracted every consequence of the theory. The equations of quantum chromodynamics are known. The theory is precise and well-defined, but it is so rich, so complex, and so resistant to analytical solution in the strong coupling regime that physicists are still working to understand everything it implies. The difficulty is not in the theory. The difficulty is in our ability to solve it completely. And now, let us return to the question that brought us here. The question in the title. What happens when you try to pull 2 quarks apart? You now know the answer in its full physical detail, and it is an answer unlike anything else in physics. When 2 quarks begin to separate, the color field between them does not spread into the surrounding space the way an electromagnetic field would. Because gluons carry color charge and interact with themselves, the field lines are forced inward. They collapse into a narrow flux tube, a concentrated cylinder of color field energy stretching between the 2 separating charges. The energy stored in this tube grows in proportion to the distance. The force does not weaken. Every increment of separation costs the same amount of energy as the last. But the flux tube does not stretch forever. When enough energy has accumulated, the concentrated field becomes unstable. The stored energy is sufficient to produce a new quark-antiquark pair from the vacuum. This does not violate any conservation law. The energy for the new particles comes directly from the work done in separating the originals. Mass is created from energy, exactly as Einstein's equivalence predicts. The newly created quark pairs with one of the originals. The newly created antiquark pairs with the other. The single flux tube breaks into two separate color neutral hadrons. This is string breaking, and the new quarks are themselves confined. No free quark appears at any stage of the process. Color neutrality is maintained at every instant. If the separation is driven by the enormous energies available in a particle accelerator, this process repeats many times. A cascade of pair creation events produces a parton shower that hadronizes into a jet. A narrow spray of dozens or hundreds of hadrons, all flying in the same direction. Detectors observe these hadrons. Physicists reconstruct the properties of the original quark or gluon from the jet's collective energy and momentum. The quark is inferred, measured, and characterized with extraordinary precision, but it is never seen as a free particle. The attempt to separate quarks does not produce freedom. It produces creation. The energy meant to liberate becomes the raw material for new imprisonment. The harder you pull, the more matter you create, and every new particle is itself confined. You cannot win. You cannot break even. You cannot get out of the game. And this mechanism, this relentless enforcement of color confinement, is directly responsible for the mass of everything around you. Over 99% of the mass of a proton comes not from the rest masses of its quarks, but from the energy of the confined quark and gluon system. The kinetic energy of quarks moving at immense speeds inside their tiny prison, and the energy of the gluon field that binds them, together account for nearly all the mass that makes matter feel solid and substantial. Your weight on a scale is almost entirely the weight of confined energy. Confinement is not just a curiosity of subatomic physics. It is the reason you have mass. It is the reason the material world exists in the form you experience. There is something deeply strange and deeply beautiful about this picture. The atoms in your hand are built from protons and neutrons. Those protons and neutrons are built from quarks and gluons. The quarks have almost no mass of their own. The mass you feel when you press your hand against a table is almost entirely the energy of color fields and fast-moving quarks, trapped inside those protons and neutrons by the same mechanism that prevents you from ever pulling a quark free. Every object you have ever touched, every planet you have ever stood on, every star you have ever seen in the night sky, owes its mass, its substance, its physical reality to the confinement of color charges. The mechanism that makes quarks impossible to isolate is the same mechanism that makes the material world massive and tangible. Confinement is not a limitation. It is the engine of reality. And the most humbling part is this: we know it works. We can calculate it. We can simulate it. We can test it to extraordinary precision. But we cannot yet prove, with the full rigor of pure mathematics, that the equations of quantum chromodynamics necessarily demand it. We stand in front of a door that is clearly locked. We can describe the lock. We can explain what it does. We can observe that it has never opened. But we have not yet written the proof that explains, from first principles, why it must always remain closed. This is where one of the most important results in physics meets one of its greatest open challenges. Confinement is an empirical certainty and an analytical mystery. It is simultaneously one of the best tested predictions in science and one of the least understood from a purely mathematical standpoint. So the next time you pick something up, the next time you feel the weight of an object in your hand, remember what you are actually feeling. You are feeling the resistance of confined energy. Energy locked inside protons and neutrons by a force that tightens when you pull. A force that creates new matter from its own tension. a force that has never once in the entire history of experimental physics allowed a single quark to escape. This is, in the end, a story about what the universe will not allow. Every other barrier in physics can be overcome with enough energy. Heat a solid and it melts. Heat a liquid and it boils. Ionize an atom and the electrons fly free. Split a nucleus and the protons and neutrons separate. At every level of matter's organization, there is a threshold, a price of admission. Supply enough energy, pay that price, and the structure yields. The components come apart and go their separate ways, but confinement breaks this pattern completely. Supply more energy to a confined quark, and you do not approach a threshold beyond which the quark escapes. You approach a threshold beyond which new quarks are born. The energy you intended as the price of liberation becomes the raw material for additional confinement. The system absorbs your effort and uses it to multiply the very thing you were trying to undo. There is no amount of energy, no level of force, no conceivable technology, present or future, that changes this outcome. The rules are written into the structure of quantum chromodynamics itself. They are not engineering limitations waiting to be solved. They are laws of nature. And yet this imprisonment, this total absolute refusal to release a single color charge, is not a flaw in the design of the universe. It is the design. From this unyielding confinement comes everything. Every sunrise you have ever seen was powered by nuclear reactions inside a star. Reactions between hadrons whose mass comes from confined energy. Every breath you have ever taken filled your lungs with molecules whose weight is overwhelmingly the energy of trapped quarks and gluons. Every heartbeat that has ever kept you alive was driven by chemical processes between atoms whose substance is almost entirely the product of confinement. The quarks cannot escape. Because they cannot escape, the energy stays. Because the energy stays, protons have mass. Because protons have mass, atoms have weight. Because atoms have weight, stars ignite, planets form, oceans fill, and on at least one small world orbiting one ordinary star, someone can look up at the sky and wonder what would happen if you tried to pull two quarks apart. The answer, as it turns out, is that you would create the very substance you are made of. The act of pulling is the act of creation. The universe's deepest prohibition is also its most generous gift. You are not holding matter in the ordinary sense. You are holding a consequence of confinement, a piece of the universe's deepest refusal to let go.